So here's something I see a lot. Developers build an AI feature, it works great in demos, and then it completely falls apart on real world tasks. The agent hallucinates, loses context, tries to do too many things at once. And the instinct is to make the prompt bigger, add more instructions, maybe switch models. But that's not really the problem. The problem is the architecture. Single agents are fundamentally limited. What actually scales, what the big AI systems you interact with every day are built on, is something called the multi agent architecture. And that's what we are breaking down today. Think about what you're actually asking a single agent to do when you give it a complex task. Research this topic, write a summary, generate some notes, check if the code is correct or not, format the output, plan next steps. So that's five completely different cognitive jobs, and you're asking one thing to context switch between all of them, maintaining state across all of it in a single context window. It's like hiring one person and asking them to be your researcher, your developer, your QA engineer, and your project manager simultaneously. So it doesn't work for humans and it doesn't work for agents either. Multi-agent systems solve this by splitting the work. Instead of one agent doing everything, you have multiple agents, each with a specific role, coordinated by a central brain called the orchestrator. So the orchestrator doesn't do the work itself, it plans, delegates, and assembles. The workers are the ones actually executing the task. And specialists are highly optimized agents brought in for specific domains like a dedicated code review agent or a database query agent. So think of it as moving from solo freelancer to a coordinated team. So the orchestrator is the most misunderstood piece of this. People think it's just a router that it reads the input and forwards it to the right agent. So that's a really shallow view of it. A good orchestrator does three things. First, it decomposes the task. That is, it breaks a complex task into smaller subtasks that can be executed independently or in parallel. Secondly, it routes those subtasks to the right agents based on what those agents are good at. And thirdly, this is the part most people actually underestimate, is that it synthesizes the results. It takes output from five different agents and turns that into one coherent response. The orchestrator is basically a project manager that never sleeps and never miscommunicates. Okay, so conceptually, this all makes sense, orchestrator, worker, specialist, but how does this actually look in code? How do agents communicate, and how do you prevent one agent's mistake from cascading into everything else? So let's get into the actual patterns. Worker agents operate on a task queue model. The orchestrator pushes tasks into the queue. Workers pull that from the queue independently and in parallel. So this is huge because it means your system scales horizontally. So if you've got 10 tasks, spin up 10 workers, and if one worker fails, the task requeues and another worker picks it up. So this is the same pattern you would use in a distributed system for background jobs like Celery, BullMQ, except instead of processing image uploads, your workers are calling LLMs. The mental model is pretty identical. Now, specialists are where this gets really interesting. A specialist agent isn't just a worker, it's an agent that's been heavily optimized, often fine tuned, or given very specific tooling for one narrow domain. A code review specialist has a system prompt built around clean code principles, knows your code based conventions, maybe has access to your linter tools as well. A SQL specialist knows your schema, your query patterns, your performance constraints. So you would never ask your code reviewer to do an SQL optimization, and you shouldn't ask your agents to either. So specialization is what unlocks accuracy. There are two main ways agents talk to each other, and choosing the wrong one kills your latency. The first is sequential, also called as a pipeline, where agent A finishes, passes output to agent B, B passes to C, and so on. This is simple to reason, but it is actually pretty slow. Every step blocks the next. The second is parallel fan out, where the orchestrator sends tasks to multiple agents simultaneously and waits for all of them to finish before synthesizing. This is faster but harder to manage. You need to handle cases where one agent takes way longer or one fails. So most production system uses hybrid, where some steps must be sequential and others can be parallelized. Here's the thing nobody talks about in multi-agent tutorials. So what happens when an agent fails? Because they will fail. An LLM call might time out, an agent hallucinates an output in the wrong format, and the next agent can't parse it. A tool call returns an error. So you need layers, right? The first is retry logic. Most transient failures resolve on retry. Second is fallback agents. So if your primary summarizer fails, you gotta rotate to a backup. Third, and most importantly for high stake systems, human escalation. Some failures should not be silently retried, they should surface to a human immediately. Good multi agent architecture is as much about failure paths as happy paths. So let me make this pretty concrete. Say you're building an AI research assistant. User asks a complex question, the orchestrator breaks it down. It sends one agent to search the web, another to read internal documents you've uploaded, and the third to pull structured data from database, all in parallel. Once all three return, the orchestrator passes everything to a synthesis agent whose only job is to merge and summarize. The synthesis agent's output goes to a fact checker specialist that flags any contradictions or unsupported claims. The final answer reaches the user. So this whole pipeline can run in under 10 seconds. No single agent would reliably do this well. This is important. Multi-agent is not always the answer. If you are building a chatbot that answers simple factual questions, a single well-prompted agent is faster, cheaper, and less failure-prone. Multi-agent systems add latency, that is, every handoff between agents adds time. So they add cost, more LLM calls means more tokens, and they also add complexity because debugging a pipeline across five agents is genuinely hard. Use multi-agent when tasks genuinely require parallelism, specialization, or too long to fit in one context window. So don't use it just because it sounds more impressive. Where this is all heading is autonomous agent networks. That is, systems where orchestrators themselves can spawn sub orchestrators, where agents have persistent memory across sessions, where the whole network adapts based on what worked and what didn't. So, OpenAI's Operator, Anthropic's work on Claude Agents, Google's Project Astra, these are all moving towards this vision. We are still pretty early here. A lot of tooling is immature. The failure modes are poorly understood. But if you understand orchestrator, worker, and specialist patterns, you already understood the foundation of everything that is being built on. Alright, so let's wrap it up. Multi-agent systems work because they mirror how real engineering teams work. You don't hire one person to do everything. You build a team with clear responsibilities, and the orchestrator is your tech lead. So workers are your engineers, specialists are your domain experts you bring in when things get pretty complex. And if you're building anything serious with AI right now, understanding these patterns is non-negotiable. If this clicked for you, please subscribe. And I post regularly on AI engineering and system design. And there's a lot more of this coming. So see you in the next one. Thank you.